Hello, my name is Brent Bollert. In this presentation, I will be giving a primer on river basin modeling in the ECRAI framework. We'll begin by giving a quick overview of catchment management planning and then moving into some alternative water systems modeling frameworks, and then focus specifically on the water evaluation and planning tool that was used in the ECRAI work. To start, imagine that you're developing a catchment management plan. In the process of doing this, you're considering a range of possible development strategies. How do you go about choosing among them? So clearly it's important to consult stakeholders and policymakers, but by themselves, they will not be able to provide us with quantifiable metrics comparing one strategy against another. So one way we might go about doing that is by incorporating all of these different interventions and strategies into a systems framework. In the top right, we see an example of a systems framework. This is a Mike Hydro systems model that links water flowing through rivers to different types of development activities and different investments in the system, such as reservoirs and demand nodes and environmental flows, and allows us to actually evaluate these kinds of questions from a quantitative perspective. In terms of different types of modeling tools in river basin planning, we need to employ crop models to evaluate impacts on yields and water demands by agriculture, rainfall runoff models to understand linkages between climate and runoff, river network models, such as the ones we'll be discussing in this presentation, and lastly, economic models to evaluate impacts from a monetary and economic perspective. Now, modeling tools become even more critical when we're planning for climate change and variability. Now, these mean a future that cannot be evaluated based on historical observations. What we have observed in the past is not enough to tell us about what the future will be. So as a result, we have to simulate the future using some kind of a modeling framework. One of the most important modeling tools in river basin planning is the water system model, which will be the focus of the rest of this presentation. There are a range of different alternative modeling approaches available, one of which is Mike Hydro. This model is a simulation model based on user-specified sets of prioritized operation rules. WEAP, or Water Evaluation and Planning, on the other hand, requires fewer rules to be user-specified and instead has an optimization algorithm that assigns priorities and allocates water that way. It's excellent at scenario analysis. Riverware requires the most user input, requires detailed specification of rules, but also allows for incredibly detailed modeling of elements of the hydrological system like hydropower. There are various strengths and weaknesses of each of these models. So which model did we end up using in ECRAI? We ended up choosing the WEAP model because of its transferability and flexibility and the fact that in a relatively data-poor environment, it did not require as many user inputs. Now, this slide represents the overall modeling system of the ECRAI process. We have climate information and climate projections entering the water system model, which generates information on infrastructure performance. Investment information is fed into both the water and the energy models. And then there's interaction between the energy and the water models that will be discussed in a later presentation in this series. Ultimately, this all drives towards economic cost estimation and estimation of the present value of hydropower and irrigation investments. The geographic focus of the water analysis is the 7 major river basins shown on this map. It includes the Nile, the Congo, the Zambezi, the Orange, the Niger, the Volta, and the Senegal. Each of these 7 basins has its own WEAP that is available through the data warehouse. So what is the Water Evaluation and Planning System, or WEAP? It is used in 171 countries and a widely accepted tool used in thousands of projects since it was developed in 1990. In the bottom left corner of this slide, you can see a URL link to try WEAP in a tutorial And this tutorial lasts about 1 hour. It's a very user-friendly program, and this would be a good way to get introduced to the software prior to diving into the data warehouse and downloading the WEAP models themselves. This slide shows the interface of WEAP using as an example the Volta River Basin, which is located in Western Africa, as you can see on this map on the left. Now, the right side of this window, this WEAP window, shows the Volta River Basin itself with a whole series of rivers and sub-basins. On the far left of the window, we have a bar that shows the schematic, which is what we're looking at right now. That's the map. And then a data pane where we can navigate through different data elements. Results presentation, those 3 colored bars. And then what's called the Scenario Explorer that allows you to look at different types of results and compare results under different scenarios. And finally, notes where you can keep record of some of the details and comments that you might have about the different elements of the WEAP. Just to the right of that, in the top left, we have the different objects. So you can see here, for example, there's a river, diversion, reservoir, groundwater, demand sites, catchments, etc. And each of these are different shapes. They're either a triangle, a square, a diamond. In the case of river, it's a line. And you can simply take these within WEAP and drag them into the map that you create to build up this network of different objects that are connected to each other by way of the rivers. Below that, we have another small window that shows the different shapes that you're portraying. So in this case, Volta Lake is included, the river system, which is a background image, and the subbasins are all included as well. And then below that is a map that you can zoom out further on to show a much larger region around the Volta Basin. So you could potentially show all of Western Africa just to get some type of a frame of reference of the overall picture. Now, if you look over to the right, the blue lines represent the rivers that are built into the WEAP. All the different colored shapes represent the subbasins, the subcatchments themselves within the Volta. And then those different nodes, the circles and the squares, represent different objects. Squares are catchments. That's where the water is generated through flow and runoff. The red circles are abstractions, so water is taken out of the rivers and then returned into the river. And the triangles represent the reservoirs, where water is stored over time and used for either hydropower generation or storage to transfer water from wet times of the year to dry times of the year. One of the main goals of water resource planning is to allow us to evaluate trade-offs between water uses. We have water demanded by agriculture, water for nature, ecosystem maintenance, domestic water, water for industry, and water for recreational activity. Each of these activities requires a different amount of water, so a different quantity of water, different level of water quality, and also different timing of inflows. A systems tool such as WEAP allows us to evaluate the trade-off between these different uses. So a water resources planning model, or a water resources systems model such as WEAP, allows us to address several critical questions. And 3 are presented on this slide. The first, how should water be allocated to various uses in times of shortage? So there will be instances of drought, and during those drought periods, how should we allocate the unmet demand, meaning not all demands will be able to be fully met, and so how do we allocate the unmet demand to different uses? Another is how should infrastructure in the system, such as dams and diversion works, be operated to achieve the maximum benefit? So an example here would be a hydropower facility that also stores water for downstream supply. How do we ensure reliable supply while also maximizing generation of hydropower? And then lastly, and this is where scenarios get involved, how will allocation operations and operating constraints change if new management strategies are introduced to the system? So for example, if we decide we want to prioritize environmental flows downstream and we want to allocate some percentage of the flow to that purpose, that means that other uses upstream are going to have to be adjusted somehow. A water systems model allows us to analyze that. So to quickly provide a frame of reference for why a water systems model is so important, So this figure shows the infrastructure expansion plans under PETA+, under the PETA+ investment scenario, in the SAPP basins, that is the Zambezi, the Orange, and the Congo. The blue bar is 2010, so that represents 100% of 2010 infrastructure levels, and the red bars represent the increases that are planned under PETA+ through 2050. So under hydropower, we're expecting a roughly 75% increase in overall capacity in the SAPP. Irrigated area, we're expecting nearly doubling of irrigated area, so a very large increase in agriculture and irrigation. And storage, we're actually expecting nearly a tripling of storage within the system. So what WEAP allows us to do is construct all of these different elements into the system and then evaluate how these infrastructure plans perform under a range of different climate change scenarios. To summarize, we started off talking about catchment management planning in general, and then moved over to looking at different water systems planning tools, which included MikeHydro, WEAP, and Riverware, and then moved on to focusing on the tool that is used in the ECRAI work, which is WEAP, Water Evaluation and Planning System. And then from there talked about some of the key questions that this tool helps us to address. Thank you for your attention.